Okay, so this will be the help for 3.3, where we're talking about conservation of energy problems and more specifically the non-conservative forces and how that impacts the situation. You guys are doing 2, 3, 4, and 5. I'm just going to go through and work on the setup for 4 and the setup for 5. I'm assuming you can work through 2 and 3, but you'll see how that goes. On question number 3, we're given that the projectile has a mass of, sorry, not 3, I want to do 4 and 5, or 5 and, 4 and 5. Jeez, Mr. Welch, get it right. All right, let's look again. Number 4 says there's a non-conservative force pulling a 1,500 kilogram car up a mountain road. It's doing 4.7 times 10 to the 6 joules of work on the car. Let's just be really clear. Something is pushing the car up the hill, and it is doing a certain amount of work. So there is work being added to the system, or an applied work. It's being added into the system. Originally, the car sits at rest at sea level, which means that the potential energy at the beginning is 0, and the kinetic energy at the beginning is 0. There is no energy in the system initially. Okay, there's my fancy looking car. Doesn't matter. Actually looks a little bit like a face. Okay, it's going to go up a hill. When it gets to a certain point, we're told that the velocity of our car is 27 meters per second, and it had a height change or an altitude change of 200 meters. Now, obviously at this point, it has potential energy, it has kinetic energy. But if that energy doesn't add up to the input or the work by non-conservative force, but we're going to call it an applied force, so work that's been applied, which is 4.7 E6 joules. If I don't have that much work in the system or much energy in the system at the end, then some of it disappeared. And so when we set this up, what we're going to do is we're going to say that the work applied, or the applied force, and the work that it produces, the energy input, minus any work by non-conservative forces like friction or air resistance. Okay, so this is our friction and air. Okay, friction or air resistance. So we have what we put in, minus any losses along the way, should equal our potential energy at the end plus our kinetic energy at the end. So this is a balancing of the equation. We know that applied work came out to 4.7 E6 joules minus WNC. Now, if it turns out that potential energy and kinetic energy add up to the 4.7 E6, that means that there wasn't any losses due to friction and air resistance. So this could be WNC is 0, but the only way to know that is to see what actually happened. With the potential energy, it's always the mass. I don't have the mass in front of me. Let's go back. The mass of the car is 1,500 kilograms. There we go. So it's 1,500 times gravity, which is 9.8, times the height, which ended up being 200, plus 1/2 the mass, 1,500, times the velocity, which was 27, and we square that last number. We square the velocity. So over here on the right, this is all big calculation. I'll grab my calculator. Let's run those numbers. 1,500 times 9.8 times 200 plus, I get to add the kinetic energy, 0.5 times 1,500 times 27 squared is 3,486,750. That is not as big as my 4.7 E6. 3486750. 3486750. If I have that number written right from my calculator. 6750. All right. This is what we ended up with in terms of our energy on the right. So our 470000, yeah, joules minus something took energy out of the system, because we're not as big as we were before. So real quick swap around, we're going to move that over and we're going to subtract that back. So we'll add the work by non-conservative forces. The work by non-conservative forces, what's being removed from the system, is the difference in these two numbers. And I'm just going to subtract 4,700,000. Ooh, that looks right. And I get negative 121.3250. Negative 121 joules. So we see that we're coming out with a loss, okay, of 1,210,000 joules. And I think that should come out right. Negative 1.21 times 10 to the 6th. Same value there. All right, now as we look at question number 5, our other problem that we want to deal with the setup, they give us a nice picture and everything, but let's be honest, we still have to try to figure out how to interpret what we're seeing. And this isn't inherently difficult if you're good with what we've already done in other sections, but I understand the complexity of it. Okay, there's our angle of 35 degrees. This is 2.5 meters. We want to know how fast the person's moving at the top of the hill. We know that there's some velocity down here. We know there's obviously a rise of 2.5 meters. We also know that the coefficient of friction for the skis on the snow is listed at 0.08. In terms of sig figs, this question is set up to be a 3 sig fig answer. Let's grab a couple of these other numbers. The mass of the skier is 60 kilograms. The V1 is 12 meters per second. What else do we got here? And it's 2.5 meter rise. Okay, that's really all that we need to be able to work through this problem. We have to understand this before and after scenarios. At the beginning, there is no potential energy because we're going to assume that the person's at a height of 0. But we do have kinetic energy 1. And we have to acknowledge friction is taking some energy out of the system. So we're going to minus the work by non-conservative forces. Specifically on this problem, we're thinking of that as friction. And that should equal the potential energy plus the kinetic energy at the top of the hill. We know there's some losses, but hopefully it's not too much, and skier can still be moving pretty quick when they get to the top of that hill. But as we start this, we're going to go through and just fill out what we do know, and then look at what do we have left to find in order to make it work. So kinetic energy is typically 1/2 mv squared, a mass of 60, a velocity of 12, and we square that value, minus. Now I don't know how much work is being done, but because it's friction, I can replace the work with the formula for work. You see, if I knew the final speed of the skier, I could actually just solve for WNC, get a number, and I could work on it. Here, I actually don't know WNC. I just know that friction is taking something out. Well, the formula for work is force times distance. Now, a couple things. What is the force that's applying this slowing or this loss of energy? And it would be the force of friction. The distance would be this distance here from the bottom to the top of the hill along the incline. That's going to be something we're going to have to calculate. So we're going to figure out how much friction is working on the skier, and then also what is D. Friction is not just the 0.08. That's just a piece of the puzzle. We're going to have to come back to that to figure a lot of that stuff out. But over here, potential energy, that'd be our mass, again, of 60 times gravity, 9.8, times the height change, which is 2.5, plus 1/2 the mass, which is 60, times the unknown V2, which needs to be squared. So when I look at this, I've got 3 different unknowns. I don't know the final velocity, but guys, that's what I'm looking for. So I'm not going to try to find it by some other method. And then I have this force of friction and the displacement, or the distance traveled. I think both of those need to go back up to the diagram to solve them. So I'm going to look at my diagram, maybe just specifically for gravity, or for friction. So if I think about the skier along their way, you know, we have mg, mg cosine theta, and mg sine of theta. Of course, we have Fn, and because the skier is going up the slope, we actually expect the force of friction to be down the slope. Okay. Now, by default, the formula for the force of friction is always mu times Fn. But we know that Fn will have to equal mg cosine theta. So that allows us to say that the force of friction is mu mg cosine of theta. So that's going to allow me to bring that information over where I see the force of friction. Now I know mu, I know mass, I know gravity, and I know the angle. So that's all known stuff. I can plug into the formula here. The last piece is, what's this distance? We come back to this drawing here, and we think about this right triangle. We have a 35-degree angle and an opposite side of 2.5. To find the hypotenuse, which would be my distance, I'm going to use sine. So the sine of 35 would equal the opposite 2.5 over the hypotenuse. We'll call it d, because that's the distance that we're going to travel. And if you haven't been in my class before, let me just introduce you to one of Mr. Welch's favorites. When we have a problem like this, we're going to swap the sine of 35 for d to get d is 2.5 over sine of 35. I like to call that the old Welcheroo, a little switcheroo that goes on there. And so that can be calculated really quickly. And there's a lot of this that could be calculated a piece at a time. This is one where I just want to know the distance. 2.5 divided by the sine of 35. Always make sure your mode's correct. In this I get 4.3586. I think I'll probably go about that far. And my distance, 4.3586. 4.3586 meters. So now when I come back to the original problem, I have 1/2 of 60 times 12 squared minus force of friction is mu 0.08 times m, 60, times g, which is 9.8, times the cosine of the angle 35. I still need to multiply by d here, so times my 4.3586. That's all on the left side. That equals 60 times 9.8 times 2.5 plus 1/2 of 60 times v2 squared. The rest of this is algebra. If you just start evaluating stuff, simplify stuff down along the way, like I'd probably clean that up, even clean this up, and then start peeling the layers. This is all one big number. Start peeling those layers, you should be able to find v2. So I'm going to stop there, let you finish the algebra part of it. But good luck, and hope that's good.